Hey! One of the most difficult things about trying to do maths on YouTube is that quite often when you're doing maths, you want to be able to draw stuff and talk to people at the same time. And unless you've got a friend to kind of switch between the camera angles, then it's really, really difficult. And, if we had friends, we wouldn't be doing maths on YouTube now, would we? So I've managed to make kind of a rig to do this, and it only uses a little bit of duct tape. The camera angle might change a few times, but it'll be fine. At the start of my holidays, I went charity shopping and I got myself a book, and I've absolutely fallen in love with this book. It is kind of difficult not to fall in love with a book that comes with its own floppy disk, and it's exactly the same age as me, which is also cool. So this book is called Nonlinear Dynamics, Chaos and Fractals with Applications to Geological Systems, which I thought sounded really cool and I had no idea how cool it was going to be. So I'm just going to take you through one of the chapters in this book, which is about calculating fractal dimensions, which is something I've wanted to do for a while, and I've read a few other books on fractals and I've still never quite got how to calculate fractal dimensions. But this one is so the geologist can understand, and I do actually understand, even though I'm supposed to be a mathematician. I imagine step number one would be knowing what a fractal is and what a fractal dimension is. First of all, fractals to most people will be kind of like a repeating pattern, things that go on and on and on, but with this cool property that it's self-similar. So the bigger parts look like the smaller parts. Think about a fern. You get the fern bit, but each of the leaves also looks like a smaller fern, and also looks like they're split up into even smaller ferns. Not all fractals have that self-similar property, but it's a good way of getting a gist of what a fractal is. Next, we should talk about what a fractal dimension is. So it's basically the same as a normal dimension that you're used to. Like, we live in the three-dimensional world and we have various different shapes you'll be used to. So in 2D, you could have a square. In 3D, you would have a cube. In 4D, you would have a tesseract, or even a weird shape like a Klein bottle. But fractals, they sit in between the dimensions. There's been plenty of times where I have tried to, in the 3D world, draw a 2D fractal, and it's impossible because you can't keep drawing forever and ever and ever. So it isn't really a 2D shape, it's not really a 3D shape. A fractal has a decimal dimension. The higher the fractal dimension, the more chaotic and fractally the fractal is? Now, today we are going to look specifically at one of my favourite fractals, which is the Koch curve or Koch snowflake. I've drawn one of these before, made out of Koch snowflakes. The curve, it would be the line all the way around the outside. And how we're going to do this today is we're only going to use really high school math. Right now we're in the home of logarithms, Scotland. Way. So if you know your log laws, you should be able to keep up with this calculating the fractal dimension, although I do have to point out the thinking that's going on behind it is, it's not even more than high school or university level, it's just different. You just have to have a different way of thinking about things sometimes for maths. So this wonderful, rapidly becoming my favourite book gives us an equation for calculating the length of a fractal, or the outside of a fractal. And this is the equation here. We've got the length according to delta, which is kind of the measurements which are on your ruler. We will talk about delta a bit more, but you decide delta. That was always the bit that tripped me up. It was like, how can it be an equation where I decide what goes in there? But there's kind of a fine art to deciding your delta. So the length, measured with your ruler, which has measurements delta, is equal to some constant, which you also decide, divided by delta, to the power of the fractal dimension. That's the bit that we're going to be really interested in. Take away 1. Basically, our plan of attack is we're going to try and fill in all of the parts of this equation so that all that's left is d here, the fractal dimension. Rearrange it, and then we will find out what the fractal dimension is. Let's jump on it. Pointing the camera to paper mode. Yeah. So as you can see here, I've attempted to draw a Koch snowflake or Koch curve. It's actually a pretty good demonstration of a chaotic system, because right at the very beginning I made this triangle and this triangle way too small, and it's had pretty disastrous effects going forward in the iterations of this curve. But use your imagination, imagine it looks good. And remember that what we are interested in is the outside, so not the inside part of this, just the curve around the outside. Were this a perfect Koch snowflake, then it would have a sixfold? Yeah, sixfold symmetry. So what I'm going to do is I'm basically going to work out the length of one of these sides and then times it by 3 rather than working out the length of the whole thing. And once we've got the length, then we will have the left-hand side of our equation. So let's just think this through in an iterative kind of way. So in the first iteration, the length of one of the sides is just going to be one side of an equilateral triangle, length 1. Then I'm going to basically take the middle third and put another equilateral triangle on there. Now I've got all of these bits are length 1/3. And then for my third iteration, all of the bits which are length 1/3, I'm going to cut the middle third out of those, a third of a third, so a ninth out of those, and make another equilateral triangle. Chop, chop, chop. And all of those are 1/9. So here's a bit I know you've been excited for. We finally get to understand delta, this mythical ruler part in our equation. What delta is which measurements you need on your ruler so that you can accurately measure the length of your fractal. And that's obviously going to change depending on which iteration you're on. For example, on the first iteration of our fractal, I really only need a ruler that measures 1. First iteration, this would be a fine ruler. It goes 0 to 1. My delta here could just be 1. On the second iteration, if I try and measure this with the same ruler, just a unit ruler, I would have to do some guesswork. I wouldn't quite be able to do it. It would be really useful to have 1/3 marked on my ruler. So for the second iteration, I would like that to be my ruler so that I can accurately measure, oh yeah, that's a third, that's a third, that's a third, that's a third. My delta would be 1/3. I think you probably see where this is going. By the time I get to the third iteration, 1/3 doesn't cut it anymore. I can't quite, I'm trying to check, is that a ninth? I don't know. It would be really helpful if I had 1/9 marked on my ruler. For the third iteration, my delta would be 1/9 and my ruler would look like that. We're going to define our delta to be 1/3 to the power of p, and p is going to be the number of iterations that we are along. This is our 0th iteration. 1/3 to the power of 0, anything to the power of 0 gives me 1. Excellent, my ruler is 1. On this iteration, 1/3 to the power of 1. Yep, that would give me a third. Cool. 1/3 squared would give me 1/9. So my delta, which I've just decided myself, but I've reasonably decided, is going to be 1/3 to the power of p. I always used to just fry my brain thinking, well, if I get to choose it, why can't I choose anything? My lecturers would say, well, you've got to pick a reasonable delta. Who's to say what's reasonable? It's, if you really think about it, some things are reasonable and some things are not. So this is our reasonable delta. Just going to put in here which iterations these are. So 0th iteration, first iteration, second iteration. Let's actually work out the length. Let's use our ruler. So our first one, the length of this bit, quite easy to see. Ooh, what is this? It is 1. Our next one, each of these sections is 1/3. How many of those have we got? 1, 2, 3, 4. Okay, 4 of them, 4 lots of 1/3. That's going to give me 4/3. So that's my length here. This one over here, we're now using our delta is 1/9. How many of those have we got? 1, 2, 3, 16. 16/9. I think it pops out at you. 16, 9 square numbers is 4/3 squared. So we're starting to get a pattern here. 1 could be anything to the power of 0. Maybe it's 4/3. 4/3 is 4/3 to the power of 1. 16/9 is 4/3 squared. I think we've got sufficient data now to conclude that the length of these parts here is 4/3 to the power of p. But remember, we've got 3 sides on our Koch snowflake, so we're going to have to do 3 lots of that. Oh no, I've run out of space. This is why maths should always be done on a blackboard. We'll act like nothing ever happened. The length in terms of delta is going to be 3 lots of 4/3 to the power of p. Okay, so it's always good in maths to kind of remind yourself of your original plan of attack. If you remember, we had this equation here, don't ask me to derive it. We were going to substitute in as much as possible and hopefully just leave d out, and then that way we can figure out what d is. So currently, we have worked out that the length in terms of delta will be 3 times 4/3 to the power of p. We've defined delta to be 1/3 to the power of p, and then that will also be to the power of d minus 1. All we've got left to fill in is this constant here, which we also get to choose 3. Pourquoi? Because our original p0, like the very first iteration of the Koch snowflake, would be length 3, so it just seems like quite a reasonable constant to choose. And now we're at the point which actually inspired me to make this video. I'll show you the line in the book. Everything that we've done so far fits into this one paragraph here, and then across the page we get some nice pictures, but then it also has this line here. The fractal dimension d must satisfy the equation which we have just worked out, from which it follows, after taking logarithms to any base of both sides, that d is equal to, and then the answer. When I was reading this, it did not just follow to me that doing logs of both sides of that would give me the answer that's got written there. So the answer that we're aiming for, spoiler alert, is log 4 over log 3, which is really nice. You know, it harkens back to the length of the side. It's very clean. It's a nice fractal dimension. But looking at the equation that we've got, it did not immediately occur to me that would be the case. So I thought to myself, you know, I'm going to take the logarithms of both sides of that equation and see if I can get that answer, which is really good practice in maths when it says it follows, to actually go through it and see if you can follow. First time I did it, I made a really rookie error very early on. Drastic camera change so you can actually see what's going on. I said first time I did it that I made a rookie error, but actually the first and the second time I did it, I made 2 very similar rookie errors, which is why it is much darker now than it was a second ago. There's a lot to be said about massaging this right-hand side of the equation a bit first before we take the logs, because look at it, it's an absolute mess. It is a fraction, it has a fraction with a power to another power, which I have turned into a times. This is just a little side note looking at what we can do to kind of mold this into something which will actually be helpful. Which is why it's in a different colour. I don't know why I can never start a sum without writing down either the original equation or the bit that I just started with. First thing that I don't like is the fraction and the fraction. The fact there's a power here and a 1 on the top. So what I'm going to do, right, we'll keep the 3 on the top over 1, because 1 to the power of anything, even p to the d minus 1, is still 1, over 3, and then we've got our p to the power of d. So now I have a fraction with a fraction on it. If you divide by a fraction, it's the same as multiplying by the reciprocal. So if I flip this round, it's just going to have a 1 on the bottom. Basically multiplying by the reciprocal, I get 3, this is my 3 from the top there, times 3p to the power of d. And if you do a power of a power, make that more p-like. If you do a power of a power, it's the same as timesing those 2 powers together, which is why I'm within my rights to do this here. And technically this is over the 1 there, but nobody shows 1 as a denominator. So this is what I am going to use as my right-hand side of the equation when I take the logs. Okay, we're back here. Let's put in what we just learned there. So I'm going to have 3 4/3 p, and you might say to yourself, hey, why not turn this 3 times 4/3 into a 4 and just have 4 to the power of p? Well, my friend, BODMAS is the reason, and that is one of the several rookie errors which I made whilst trying to calculate this. The second rookie error I made was then, once realising that I couldn't just times these together for BODMAS, I then also made the mistake of not noticing that the p only applies to this 4/3. So remember that this power is only here, and these 2 things are not really multiplied together. It's this times this. Little rant over. So we've got 3 times 3p d minus 1. Are you ready? Are you ready for logs? Yes, I am. Oh, yeah. Log p equals log 3 times 3 p d minus 1. Woo! Now we've taken logs of both sides, just like the book told us to. But if the book had not told us to, how could we have known that what we were supposed to do is take logs of both sides? The hint is in the power. If your variable that you are looking for is a power, then really your only option is to take logs to try and get that power down using your log laws. Let us use our log laws. I'm going to use the rule that says when you've got two things times together, it would be the logs added together. So that's going to give me log of 3 plus log of 4/3 to the power of p is equal to log of 3 plus log 3 to the power of p d minus 1. Now I'm going to use the rule where I take the powers down to the front. This is probably the most useful thing that logs do. That's a lie. Logs are just great for everything. Monologues. But yeah, it's really, really useful, this rule here. So I've got log 3 plus, and the p comes down, making this log of 4/3 equals log 3 plus p d minus 1 log 3. Remembering that that p is multiplying all of this. At this point, this is way too many log 3s. I mean, we need some log 3s, but not this many. So let's take log 3 away from each side of the equation. I can do that. It's not against the rules. Now, let us recap. What have we got here? P log 4/3 is equal to p d minus 1 log 3. Oh, yes. This is the moment I was really hoping would happen, like the tentative moment, because if you look right back at the start here, we're trying to get d, so we need to find it, but we've got this other extra variable in there, p, which we were really, really hoping would cancel out. And look at this. There is p on this side, everything multiplied together. Let's cancel those p's out. Bye-bye. What are we going to do from here? I'm going to take this log 4/3 and I'm going to use the dividing rule, which becomes subtract in log world. So I get log 4 take away log 3 is equal to, now with this d minus 1 log 3, I'm basically multiplying out the brackets here. So I'm going to get d log 3 take away log 3. Solving for d, because d is my only variable now. I've got this take away log 3 here. I want to get rid of that take away log 3. Opposite of take away log 3 would be add log 3. And look what's going to happen to the other side as well. So that take away log 3, that take away log 3, they're going to cancel out. And I'm now left with d log 3 is equal to log 4. And I think we can very happily follow from there that d is equal to log 4 divided by log 3. QED, yo! So there you have it. We managed to calculate the fractal dimension of a cock snowflake. Woo! In all seriousness though, I always feel like really mathsy books kind of miss a few steps out by just flippantly saying, oh, just take logs of both sides and it follows. No. It is good to go back and check that, and I hope this example has been helpful to you. There are easier ways to do this. So on the very next page of this book, it shows you how to use limits to calculate the fractal dimension, and it takes about 3 lines. But I feel like going right from the very start, looking at how to choose delta, things like that, I think it helps you understand how you get a fractal dimension, what a fractal dimension is, as well as calculating the actual fractal dimension. I said I was only going to use high school maths, and really I have done that. The only things I've used are the log laws, I've rearranged equations, I've done a little bit to do with fractions. There's nothing further than higher maths in here. Would I ever expect someone in higher maths to be able to do this? Not a chance. But you could. So I just want to finish off by reading the quote that this awesome little book starts with. It's about chaos theory, which gave rise to fractals. In this physical world, there is no real chaos. All is in fact orderly. All is ordered by physical principles. Chaos is but unperceived order. It is a world indicating the limitations of the human mind and the paucity of observational facts. The words chaos, accidental, chance, unpredictable are conveniences behind which we hide our ignorance. I think that's super cool and mind blown. Right, thanks for watching and I will see you guys later. This log 3 and this log 3, this P and this P. Huh. Why is this P still here? What have I done?